So we've been looking at angles, and now we are going to look at trigonometric functions of acute angles. So acute means that it's less than 90 degrees of a right triangle. And we're going to define the trigonometric functions that way. So in front of you, you see the learning objectives for this next section on our textbook. And so one, we want to find the values of a trigonometric functions of acute angles. We are going to learn some of these fundamental identities. There's fundamental identities in this section that we'll be using throughout this course, and then you'll also be seeing them again when you are in calculus. Number 3, you're going to find the values of remaining trigonometric functions given the value of one of them. So given a trigonometric function, maybe let's say sine theta is equal to 1/2. We want to be able to find what the other trigonometric functions are. And then we're going to look at another theorem, which is going to be helpful to us also, and it's called the complementary angle theorem. So hopefully after this lesson, you'll be able to do all of those things, or after you do the homework on this section. Okay, so let's define trigonometric functions. So definition of a trigonometric functions. Trigonometric functions are ratios of lengths of the side. So there's 6 ratios of lengths of the sides of a right triangle, and those are called your trigonometric functions of acute angles. So right now we're just going to look at them with acute angles, but next section we'll talk about when we have angles that are bigger than 90 degrees. And are defined as follows. So we have 6 trigonometric functions. The functions names are right here in front of us, and we have abbreviations for each one of these. And so we have sine of theta, and the abbreviation is SIN. We don't say sin theta, we say sine theta. And if you look at sine theta, you have to look at the angle on your triangle. So there's a triangle here with angle theta. This is a right triangle. And sine theta is the ratio of sides of opposite. So in this case, opposite is side length has opposite of angle theta has length B all over hypotenuse. So hypotenuse in this case has length C. Actually, let's put B over C here. And let me put over here ratios of sides as opposite over hypotenuse. So cosine theta, we're going to abbreviate it COS theta. And this is adjacent side. Adjacent all over hypotenuse. So if we look at locate where angle theta is, the adjacent side of angle theta is one of the sides that is sandwiching this angle theta, but is not the hypotenuse. And hypotenuse is always opposite of the right angle. So right angle, this would have to be the hypotenuse. So the adjacent side here is A, all over hypotenuse, which is length C. So tangent theta is another trigonometric function, and we would denote it as TAN, and then theta. This is the opposite side of angle theta, all over the adjacent side. Start abbreviating. So opposite of theta is side B, all over adjacent side, which is side A. Cosecant theta, you can abbreviate it as CSC theta. Cosecant theta is, I have to think about this, hypotenuse over opposite. So hypotenuse over here is length C, and opposite from angle theta is B. Secant, abbreviated as SEC. Secant is hypotenuse over adjacent. So hypotenuse is C, length C, all over the adjacent side, which is A. Cotangent theta denotes as COT theta. Cotangent theta is adjacent over opposite. So adjacent side is A, all over the opposite side of theta is B. Okay, so we need to be careful because it really depends on what angle we're looking at. So let me just kind of look at this over here. So if we had chosen the angle that's not the right angle, but the other angle on there, maybe let's call this alpha. So if that's angle alpha, the opposite of alpha is different than the opposite side of theta. So in this case, this would be opposite of alpha. This side in here, this is adjacent. Adjacent to alpha. Hypotenuse is, again, always the side across from the right angle. So that will always remain the same. Okay, so let's look at an example. And we're given a triangle in front of us. And it wants us to find each of the 6 trigonometric functions of the angle theta and the figure given below. And so we have the 2 sides of the triangle, which are called legs, that are not the hypotenuse. So we have one side that is 7, and that is the adjacent side. I just call it A, is 7. The opposite side of theta is length 5. Let's call this B. So B is equal to 5. We don't know what the hypotenuse is in this case, but recall the Pythagorean theorem. This theorem you're going to use a lot in this course, and you will also see it when you're doing your calculus. So you want to get this down, and you know, or you might know, but the Pythagorean theorem says that you're going to square the hypotenuse side. This is equal to the sum of the square of each leg. So this is equal to 7 squared plus 5 squared. This is only true, this theorem, for right triangles. So given two sides of a triangle, of a right triangle, we can always find what the other side is. And I threw in our information here, but the Pythagorean theorem says that C squared is equal to A squared plus B squared. Or C is the hypotenuse and A and B are the legs. So let's solve for C here. So we have C squared is equal to 7 squared, which is 49, plus 5 squared, which is 25. So C squared is equal to, summing this, we get 74. And taking the square root of both sides, we can find out what C is. So normally when we take the square root of both sides, we put this plus or minus here, but we're dealing with length and the length of the triangle, so we're going to ignore the negative. later on, we are going to look at that negative piece. We'll talk about that later. But, so C is equal to the square root of 74. Offhand, I don't know if there is a factor of 74 that is a perfect square. So I could look that and see by looking and rewriting 74 as prime factors, or start to write it. I see that it's even, so 2 goes in here. 2 goes into 74, let's see, 37 times. So 37 is prime, 2 is prime. They don't have any common factors that are, they don't have any factors that are perfect squares. Okay, so there's nothing I have to pull out of that radical. So now we can go and we can figure out what our trigonometric functions are. So if we look at sine theta, we're looking at the opposite of theta. So the opposite side of theta is 5, all over the hypotenuse, which is the square root of 74. So we don't like radicals in our denominator. So in this course, you're going to rationalize your denominator. So if you're left with a radical in the denominator, we can get rid of that by multiplying by a fancy one in this case. And we know that the square root of 74 squared is just going to get rid of that radical and leave us what the number underneath 74, which is called the radicand. So this is equal to 5 square roots of 74 all over 74. So cosine, and there's a way to memorize this. You might have seen this before. There's a saying that will help you remember the ratio of sides of the triangle, and that is SOHCAHTOA. So in this case, S stands for sine, that is opposite over hypotenuse. C stands for cosine, that's adjacent over hypotenuse. T stands for tangent, which is opposite over adjacent. So I know, looking at this SOHCAHTOA, that cosine of theta, this is the adjacent side of theta, so adjacent is 7, all over hypotenuse, which is the square root of 74. So quickly rationalizing my denominator, multiplying by my fancy one, square root of 74 over square root of 74. This gives me that this is 7 square root of 74 all over 74. That's what our cosine theta is. Tangent theta. Tangent theta is opposite, so opposite is 5 all over the adjacent, which is 7. So this is reduced down as far as we have it, or can have it. And so we'll just leave it like that. So the other 3 trigonometric functions, secant, cosecant, and cotangent. Let's go back up here for a second before we figure those out, and let's look at the relationship of those ratio of sides in that table that we had just created. So if we go back up here and look at our trig functions and the ratio of sides, look at the following. So looking at sine theta, this is B divided by C. And if you look over here, cosecant theta is just the reciprocal of sine theta, which is C over B. If we look at cosine theta, which was A over C, looking for the reciprocal function. Each one will have a reciprocal. So flipping our fraction, a over c is c over a is the reciprocal, and that is secant theta. So I know cosecant theta and secant theta is 1 over either sine theta or cosine theta. And the way I memorize that, and it might help you or might not, is sine theta starts with an s. So the reciprocal is 1 over the trig function that doesn't start with that s. So it would be c. So cosecant theta. So let's write that. So a reciprocal identities. We can say that sine theta, or sorry, not sine theta, that's the other trig function. We can say that cosecant theta is equal to 1 over, starts with c, so it's going to be sine theta. The other one, cosine theta. Cosine theta, the reciprocal is secant. So secant theta is the same thing as 1 over, this one starts with the letter s, so it's cosine. Tangent theta is also has a reciprocal function. Cotangent theta, b over a, opposite over adjacent. And this one is adjacent over opposite. Normally, we won't say tangent theta is 1 over cotangent theta, but you could write it that way, and you always can go in the opposite direction. Cotangent theta is the same thing as 1 over tan theta. Okay, so those are a couple identities, reciprocal identities, and we'll be using those, and I might have those written out again in these notes when we go further down. But knowing that those are reciprocal functions, we can look at those ratios of sides of those 3 trigonometric functions that we just found, and all we have to do is look at the reciprocal. The thing is, I don't want to have to undo and rationalize my denominator again. So I would probably look at, in this case, sine theta before I rationalize the denominator. So cosecant theta again is equal to 1 over sine theta. So this is equal to 1 over 5 over square root of 74. Invert, multiply. This is another way of saying 1 divided by 5 over square root of 74, just kind of reviewing a little bit of arithmetic. For your dividing fractions, you always copy down the first number. So in this case, 1 times the reciprocal of the second fraction, which is square root of 74 all over 5. So in this case, we get that cosecant theta is equal to square root of 74 all over 5. I'll erase some of this just to save some room. So secant theta again is the reciprocal of cosine theta. So it's 1 over cosine theta. So again, let's look at it before we rationalized our denominator and just flip it. So this is the same thing as square root of 74 all over 7. And tangent theta, that is the reciprocal, I'm sorry, we have tangent, cotangent theta. Is the reciprocal of tan theta. So 5/7 reciprocal would be 7. Excuse me. So given a triangle, we were able to find the 6 trigonometric functions by finding the length of all the sides, so the side that wasn't given, and looking at the ratio of sides for that angle theta. So this next example, we are given one of our trigonometric functions. We're given here that sine theta is equal to 2/5. And we're going to use the identities to find the remaining 5 trigonometric functions. So sine theta equals 2/5. So let's look at our triangle. Let's create a right triangle. And let's locate where theta is. So I could technically, if I wanted to, I could put theta up here. So if I did that, let's put our reminder of our trig function, the saying SOHCAHTOA, if that helps you. So sine is opposite over hypotenuse. So we have 2 in our numerator. That's the opposite side of theta. So going opposite of theta, this base of the triangle is 2. And the hypotenuse is 5. So we need to figure out what the adjacent side is of theta in this case. Maybe call it A. So using the Pythagorean theorem, we have c squared, the hypotenuse squared, which in our case is 5 squared, is equal to the sum of the legs squared. So we have sum square each leg and then sum it. So 2 squared plus a squared. So we have 25 is equal to 4 plus a squared. Let's get a squared by itself. Let's subtract 4 on both sides. We get 21 is equal to a squared. And taking the square root of both sides, we're talking about length. So we're going to just look at positive square root of 21. So now that we have our triangle, we can find all the rest of the trigonometric functions. So we have sine. Let's just do the reciprocal function of sine, which is cosecant. So cosecant theta. The reciprocal of that is 5/2. If we looked at cosine theta, cosine is adjacent over a hypotenuse. So looking at where theta is, the adjacent side is root 21. All over the hypotenuse, which is 5. So if we look at the reciprocal function, which is secant theta, take the reciprocal cosine theta, we have 5 over square root of 21. We want to rationalize our denominator, getting rid of the radical in the denominator. We can multiply by this fancy 1 square root of 21 over square root of 21. And so we get that secant theta is equal to 5 root 21 all over 21. And then now let's look at tangent theta. So tangent theta. Tangent is opposite of theta. So the opposite side of theta is 2. All over the adjacent side of theta. So adjacent, where I put this theta, would be root 21. So rationalizing the denominator, multiplying by square root of 21 over square root of 21, we get 2 square roots of 21 all over 21. And the reciprocal function, cotangent theta. So let's just look at the reciprocal before we had rationalized their denominator, so we don't have to redo it. This would just be square root of 21 all over 2. So not too bad. Probably the hardest thing, or the things that if you're just learning this, is realizing which angle you're looking at. And it's different between what's opposite and adjacent, depending on which angle. So just a recap of what we just saw. We have some identities here. We said that cosecant theta, this was the same as 1, the reciprocal of sine theta. So this is 1 over sine theta. Cosecant theta, this one started with S. So this is going to be 1 over cosine theta. Cotangent theta, this is 1 over tangent theta. Again, if we know what cosine theta and sine theta are, we can always get the other trigonometric identities. We didn't talk about this one yet, and we'll show why this is true, but we have what is called the quotient identity. And tangent theta can be expressed as sine theta all over cosine theta. So thinking of it, if that's true, and cotangent theta is the reciprocal identity of tangent theta, then cotangent theta is going to be cosine theta all over sine theta. So if we combine sine theta and cosine theta, we can always find the rest of the trigonometric functions. So let's prove why this identity is true. So we showed with the reciprocal identity. Let's look at the quotient identity. So let's show or create a triangle again. Right triangle. Let's say that this is theta. And opposite of theta, let's call that A. Adjacent of theta, let's call that B. And let's call the hypotenuse C. So by our Pythagorean theorem, we know that C squared is equal to A squared plus B squared. So let's look at this and let's divide every single term by C squared. So we're dividing both sides of the equation by C squared. And so on the left-hand side of our equation, C squared divided by C squared, that's just 1, is equal to, and I'm just going to rewrite A squared over C squared. That's the same thing as A over C quantity squared plus B squared over C squared. We can rewrite that as B over C quantity squared using rules of exponents. Well, if you think about this, if these are ratios of sides here, A over C. So if I'm looking at theta, A, that side is the opposite of theta, all over C, which is the hypotenuse quantity squared, plus B. So B, the side B for theta from theta, that is our adjacent side of theta in our triangle that we created, all over, and the hypotenuse is still C. Quantity squared. So those are just, again, those are trig identity, or what we defined our trigonometric functions. So opposite over hypotenuse, that is sine. So we can say 1 is equal to sine squared theta plus adjacent theta over hypotenuse. So that adjacent over hypotenuse is cosine squared theta. Okay, I just proved a different identity. So this is one of our Pythagorean trigonometric identity. So this identity, we're going to see over and over again, and we're going to see it in different forms, so it's helpful to recognize this. So sine squared theta plus cosine squared theta is equal to 1. There's 2 more trigonometric identities, Pythagorean trigonometric identities, and we can always get them based off of this identity. Before I do that, though, I want to go back up, apologize, and go back and show that this is true, at least, that tangent theta is the same thing as sine theta over cosine theta. And then I will derive those 2 other Pythagorean trigonometric identities. So tangent theta, recall that tangent theta, that was opposite of theta. So opposite of theta in our triangle that we created here is A. So tan theta is equal to A all over the adjacent side, which is B. So looking at our triangle, tangent theta is A over B, the ratio of those 2 sides. Now let's look at what this said, sine theta over cosine theta. So let's show that if we look at sine theta over cosine theta, we're going to get back A over B. So sine theta is opposite. So opposite of theta is A, all over hypotenuse, which is, in our case, C, all divided by tangent, cosine theta. So cosine theta, that is adjacent, which is B, all over the hypotenuse, which is C. We have here I need my thing. We have here a fraction divided by a fraction. And so this is the same thing as, I'm gonna give myself a little more room. Rewrite it if it helps you as division. So our numerator is A over C divided by B over C. So A over C times C over B. Since it's multiplication of fractions, we can cancel. Our C's cancel, which gives us A over B. So tangent theta was A over B, and we just saw that was the same thing as cosine theta over sine theta. No, I didn't. We said it was sine theta over cosine theta. Okay. So we had our Pythagorean identities. That was the next thing I was going to show. We just proved it over here. Up a little bit. We proved one of them. So to prove the other 2, what we want to do is we want to take the equation we just got, sine squared theta plus cosine squared theta equals 1, and we want to divide through by sine squared theta. So if we took this and we multiply both sides of our equation by 1 over sine squared theta, an equation, so we can do this. So if we distribute 1 over sine squared theta times sine squared theta, that just leaves us with 1. If we distribute 1 over sine squared theta to cosine squared theta, so this is plus cosine squared theta all over sine squared theta, is equal to, well, 1 times 1 over sine squared theta is just 1 over sine squared theta. Well, these are just some other trigonometric functions we know. Normally when we square, notice how I put the square inside before the theta? Just notation wise, that's normally where we put our exponent of our trig functions, but that's the same thing as saying cosine theta quantity squared. So technically I can take that square and say this is the same thing as sine theta. Not sine theta. It's the same thing as cosine theta all over sine theta quantity squared, which is the same thing as 1 over sine theta quantity squared. So cosine over sine, that one is cotangent. So this is the same thing as 1 plus cotangent squared theta equals 1 over sine theta. That's the same thing as the reciprocal function cosecant theta. So this is equal to cosecant squared theta. So this is another Pythagorean trigonometric identity. Okay, so one other one, again, I don't have these two memorized, but I know I can quickly derive them. And by explaining to you, it's going a lot slower, but I can quickly derive them and have them right in front of me when I need them. So let's go back to the main one, sine squared theta plus cosine squared theta equals 1. And this time, let's divide every single term on each side of the equation by cosine squared theta, or same thing as multiplying both sides of the equation by 1 over cosine squared theta. So doing that, if we have this sine squared theta plus cosine squared theta equals 1, and we're going to go through and we're going to divide each term by cosine squared theta. So sine squared theta over cosine squared theta, well, sine over cosine, that is sine over tangent. So this is tangent squared theta plus cosine squared theta over cosine squared theta is 1, is equal to 1 over cosine theta, that is secant theta. So 1 over cosine squared theta, that would be secant squared theta. So when we look at these identities, it's helpful to have them in front of us and we can use them to find different things or prove different things. So those are the 3 Pythagorean trigonometric identities. So we have some fundamental identities in front of us. Tangent theta equals sine theta over cosine theta. So these are ones that you're going to want to memorize. You should know that cotangent theta is cosine theta over sine theta. Cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. Cotangent theta is 1 over tangent theta. So we have our quotient identities, we have our reciprocal identities, and now we have our Pythagorean trigonometric identity. Sine squared theta plus cosine squared theta equals 1, tangent squared theta plus 1 equals secant squared theta, and cotangent squared theta plus 1 equals cosecant squared theta. So let's look at a couple examples that use these Pythagorean trigonometric identities or some of these fundamental identities. So the first example that we have in front of us is sine of 39 degrees all over cosine of 39 degrees minus tangent of 39 degrees. Since both of these angles are the same, let's rewrite it. That quotient trigonometric identity, sine over cosine, is tangent. So this is the same thing as tangent of 39 degrees minus tangent of 39 degrees. So tangent of 39 degrees minus tangent of 39 degrees, this is equal to 0. So pulling up the next one we have in front of us, example is cosine squared of pi fourths plus 1 over cosecant squared of pi fourths. So right now we don't know what these angles are, or cosine of that angle that's given. We'll learn those and we need to know what those are. But we can use those trigonometric identities to help us simplify this. We should be able to simplify the ones that I'm just giving you without a calculator. So when I'm giving you exams, you are going to have parts of the exams which are no calculator. A lot of times, most of the exam are going to be no calculator. So you should be able to do this stuff without a calculator. So with what we've been talking about today, I noticed that we have 1 over cosine squared of pi fourths. Well, I know that 1 over cosecant, or let's think about cosecant, we can rewrite this. So let's bring everything down. Cosine squared of pi fourths plus 1 over, well, cosecant squared of pi fourths, this is the same thing as 1 over the trigonometric function for cosecant is 1 over sine squared of pi fourths. So we can look at this second term and we can use our property of flipping our fraction in the denominator, and we would get cosine squared of pi fourths plus sine squared of pi fourths. Because these angles are the same, we're using the fact that cosine squared theta plus sine squared theta, that's equal to 1. And so we just used those fundamental identities that we talked about in this section to solve that problem. So there's a couple ways that we can approach some of these problems. We can use those Pythagorean identities to help us, or we can use the ratios, the sides of the triangles to help us. So finding the values of the remaining trigonometric functions given sine theta, and that theta is an acute angle. Let's look at the following example. And let's look at it and doing it 2 different ways. So suppose that theta or sine theta is equal to 1/2. Again, theta is an acute angle. And we want to find the value of each of the remaining 5 trigonometric functions for theta. So we're going to solve this in 2 separate ways. So let's look at the first way as using the definition of our trigonometric functions. And the second way that we're going to show or get those 5 is using the fundamental identities. Okay, so right now, we're going to use the definition. And so if you want to, we can put it in front of you if it helps you. So katoa. We want to create our triangle. When I've been doing this, these are not to scale. So theta, sine theta, remember sine theta was opposite over hypotenuse. So locating theta, theta's here. Opposite of theta is 1. Hypotenuse is 2. So we're going to use that Pythagorean theorem to find the other side. Pythagorean theorem, the hypotenuse squared, so 2 squared is equal to 1 squared plus, let's call this a here, a squared. So we have 4 is equal to 1 plus a squared. Getting a by itself, the term with a, we subtract 1. We get 3 is equal to a squared. Taking the square root of both sides, thinking of it as length. So we're going to just use the positive of the square root. So a is equal to positive square root of 3. So now going through, looking at sine theta. This is opposite. So opposite of theta is 1 all over hypotenuse, which is 2, which we already knew that. Cosine theta is adjacent over hypotenuse. So adjacent from theta is root 3 all over 2. Tangent theta, this is opposite over adjacent. So opposite side is 1 all over adjacent side, which is root 3. We want to rationalize our denominator. And so multiplying both the numerator and denominator by root 3, this is going to give us back root 3 over 3. So we can get the other 3 using the fact that they're the reciprocals of the ones that we just got. So sine theta, the reciprocal function is cosecant theta. So the reciprocal of 1/2 is 2, or 2 over 1. Cosine theta, the reciprocal of cosine theta, that is secant theta. And so that's 2 over root 3. We want to rationalize our denominator. So multiplying both the numerator and denominator by root 3, we would get 2 root 3 all over 3. And then the last one, cotangent theta. This is the reciprocal of tangent theta. I'm going to leave it in the form before I rationalized it, just so I don't have to re-rationalize the denominator. So flipping 1 over root 3, we get root 3 over 1. So we found the remaining 5 trigonometric functions given one of them. Okay, so that was by using the definition of our trigonometric functions. So we want to do the same exact thing, but this time we want to do it using the fundamental identities. Okay, so using the fundamental identities. So one of those fundamental identities, again, was cosine squared theta plus sine squared theta equals 1. Some more room. Okay, so our other method, we were given that sine theta again was equal to 1/2. One of our trigonometric identities again is that cosine squared theta plus sine squared theta is equal to 1. So using this method to figure out what, in this case, cosine theta is. So let's just go in and let's substitute in 1/2 where we see sine squared theta. That helps you, let's write it like this. Cosine theta, quantity squared, plus sine theta, quantity squared, equals 1. So we have cosine theta quantity squared plus, well, sine theta we just said was 1/2. And we're going to square that, equals 1. So we get cosine theta quantity squared is equal to 1/4. Sorry, not equals, plus 1/4. Equals 1. So we can isolate cosine squared theta on one side of the equation, and then we can use our square root. And so if we subtract 1/4 to both sides, so we need to think of this as having a common denominator when we're subtracting fractions. So 1 can be rewritten as 4/4. So we get that cosine theta squared is equal to 4/4 minus 1/4 is 3/4. Taking the square root of both sides of our equation, we get that cosine theta is equal to, well, if you have a square root of a fraction, it's the same thing as the square root of the numerator. So square root of 3 all over the square root of the denominator, but square root of 4 is just 2. So we have now what cosine theta is based off of knowing what sine theta is using our trigonometric identity. So from here, I would probably use the fact that we know that cosecant theta is 1 over sine theta. And so this is the reciprocal, which is 2. I know that secant theta is 1 over cosine theta. So the reciprocal root 3 over 2 is 2 over root 3. Rationalizing my denominator, this would give me back 2 root 3 over 3. And cotangent theta, actually, let's do tangent first. Tangent theta, we know is sine theta over cosine theta. Well, sine theta, we were given is 1/2 divided by cosine theta, which is root 3 all over 2. So we have 1/2 times the reciprocal fraction in the denominator, which is 2 over root 3. Things cancel. We get 1 over root 3. Rationalizing that denominator, we would get root 3 over 3. And the last one, cotangent theta, is just the reciprocal, put it over here, of tangent theta. Flipping it before we rationalize the denominator is root 3 over 1. I could have used the other Pythagorean identities, but to me that's a lot harder. Just knowing what sine theta is and cosine theta is, and it's just easier to use some of the other identities that we had. So let me just tie up this section we just covered. So there were that last example, we just saw that there was 2 different methods of solving the trigonometric function given one of the trigonometric functions. So method 1, give the values of one trigonometric function of a acute angle theta, the exact value of each remaining of the 5 trigonometric functions of theta can be found either 2 ways. So option 1, we looked at by using the definition. When we use that definition, First thing that we want to do is we want to draw our triangle. Draw the right triangle showing the acute angle theta. And then we're going to assign the values of the two sides based on the sides of the given trigonometric function. Find the length of the third side by using the Pythagorean theorem. And then we're going to use the definition of our trigonometric functions as ratios of a right triangle to find the value of each of the remaining trigonometric functions. So that was the first method, step by step on what you would do. The second method, given the values of one trigonometric function of an acute angle theta, it's key here that we've been saying acute, and we'll again be dealing when our angles are not acute, but things will change a little bit. Not much, but they'll change. Okay, so again, given the value of one trigonometric function of an acute angle, the exact value of each of the remaining 5 trigonometric functions of theta can be found in either two ways. The other method is using identities. So you use appropriate identities to find the values of each remaining trigonometric function. And our case, we started with the Pythagorean trigonometric identity. So recall, if you have two angles which are complementary, then those angles have to sum to 90 degrees. And so when we have a right triangle, and in front of you, you have a right triangle, notice that we have angle B here, and we have angle C. I'm sorry, and we have angle A. So a lot of times we will denote angles with capital letters. If that is the case, then the sides we will denote by the lowercase of the one that it's opposite of. So notice angle A, capital A, the opposite side here is side A and lowercase. This angle B in capital B, the side across from it is angle or side B in lowercase. Hypotenuse, we normally do with C a lot of times, not necessarily, but we do. So if that's the case, and we know that this is a right triangle, another thing you need to know is that the sum of all angles of a triangle has to sum to 180 degrees. So if this is 90 degrees, we know that these other two angles in here, that sum also has to be 90 degrees, that sum of A and B, because 90 plus 90 is 180. So we know that A plus B has to equal 90 degrees. So another way we can express this is A is equal to 90 degrees minus B, or B is equal to 90 degrees minus A. Let's look at our trigonometric functions, sine and cosine. So if we looked at sine, depends on which angle we're looking at. Let's look at sine of B. Sine of angle B, sine is opposite over hypotenuse. So the opposite of side B, angle B is side B, all over hypotenuse, which is C. Notice here, if we look at cosine of angle A, so if we're looking at angle A, sides are going to be different. So cosine is adjacent. Notice the adjacent side of angle A is side B, all over the hypotenuse, C. So sine B and cosine A, those are called cofunctions of one another. Excuse me, they're equivalent. So we can say that sine B and cosine A, but we can express this a little different. We said that here, that A was the same thing as 90 degrees minus B. So sine B is equal to cosine of 90 degrees minus that angle of sine, which is B. We can go in the opposite direction, right? We can say cosine of A that's the same thing as sine B. But in this case, B we can express as 90 minus A. So cosine of A is the same thing as sine of 90 degrees minus whatever the angle we're looking at for cosine, which is A. We can do the same thing with tangent and cotangent. So tangent, let's look at tangent of B. So tangent of B this is equal to opposite. So opposite side, or angle B is side B, all over the adjacent of angle B is side A. Or if we went to the other angle across the way, A, and do the same thing, but let's look at it with cotangent. So cotangent, I have to think about it, is adjacent. So cotangent of A is equal to adjacent side, which is B, all over the opposite side, which is A. Notice that tangent B equals tangent A, cotangent A. Or another way to write it is B is the same thing as 90 minus A. So if I did B, I would say tangent of 90 minus A equals cotangent of A. So tangent and cotangent are complementary angles or cofunctions of one another. You can do the same thing with secant and cosecant. Okay, so the theorem says complementary angle theorem, cofunctions of complementary angles are equal. So these cofunctions sine theta is a cofunction of cosine theta. Tangent theta is a cofunction of cotangent theta. And the complementary angle, though, we would look at it as 90 degrees minus whatever that other angle is. Or we can say that cosine theta, the cofunction, is sine of 90 degrees minus theta. Tangent theta, the cofunction, is cotangent of 90 minus theta. Or bring myself a little more round. You can say cotangent theta is equal to tangent of 90 degrees minus theta. We didn't show it, but secant theta is equal to cosecant theta, or cosecant of 90 degrees minus theta. And cosecant theta is equal to secant of 90 degrees minus theta. We could rewrite these. Recall that 90 degrees, we were talking about radians, is in forms of pi halves. So we could rewrite these without 90 degrees there. If we were in radians, we could write it with pi halves. So let's look at a couple of examples using these complementary angle theorem. So using the complementary angle theorem, find the corresponding function of each of the trigonometric expressions given. So we have sine of 79 degrees. So we want to look at what is the complementary angle of 79 degrees. Well, we can get that by looking at 90 degrees minus 79 degrees, which is this is equal to 19 degrees. And so here, this would be the same thing. The cofunction would be cosine of 19 degrees. So tangent of pi 18ths. So we want to find the complementary angle of pi 18ths. This is in terms of radians. And so I want to look at pi halves minus pi 18ths. So getting a common denominator. My common denominator would be 18. So I need to multiply pi halves by a fancy one, 9/9. So we got 9 pi 18ths minus 1 pi 18ths. This is equal to 8 pi 18ths. And let's reduce that. So they both have 2 in common. So that is 4 pi over 9. So tangent of pi 18ths, the cofunction is cotangent, is the same thing as cotangent of 4 pi over 9. Cosine of pi thirds. So the cofunction is sine. So this would be sine of, or in terms of radians, so 90 degrees in radians is pi halves minus pi thirds. Getting a common denominator, well, 2 and 3 is in our denominator, so our LCD is 6. And so getting common denominator, this is the same thing as sine of, well, pi halves, we need to multiply both by a fancy one, 3/3. So this would be 3 pi 6 minus, we need to multiply pi thirds by 2/2, 2 pi 6. And so we can say that cosine of pi thirds, this is the same thing as sine of pi 6. Okay, so let me give you a second. Let's throw a try it in there now. And let's have you guys try figuring out what cosecant of 5 pi 12ths is. Find the cofunction of that trigonometric expression. Just so you guys can find it easier in the video. So cosecant of 5 pi 12ths is equal to which cofunction? So I'm just going to let you guys try that. I'm going to pause the video for a second. And if you are doing this and watching the video later, you want to pause it, try it. I'm going to have you guys upload the work to this problem onto Canvas. Try it. Assignment for this week. Okay, so you should have paused the video and try that. I'm going to let you guys upload that again to Canvas assignment for this week. I'll grade it after class. Let's look at another example. So given that sine of 60 degrees is √3/2, we're going to use our trigonometric identities to find the values of, let's look at first A, cosine of 30 degrees. Okay, so this is not one that we know right now without what we're doing, but these ones right in front of you are ones that you're going to have memorized, or a lot of them you're going to have memorized later on. But cosine of 30 degrees, if we don't know what that is, we're given what sine of 60 degrees is. And I noticed that 60 degrees and 30 degrees are complementary angles of one another. So by that complementary angle theorem, I know that sine of 60 degrees is the same thing as cosine of 30 degrees. And since we were given that sine of 60 degrees was equal to √3/2, we can say then cosine of 30 degrees is equal to √3/2. So looking at cosine squared of 60 degrees. I see that I have a cosine squared in there, and that makes me think right now that cosine squared theta plus sine squared theta is equal to 1. So we know what sine of 60 degrees is. And so let's write that. So we have cosine, and theta has to be, this angle has to be the same for this identity. And so cosine of 60 degrees, I'm going to write it a little differently right now, quantity squared plus sine of 60 degrees, quantity squared, is equal to 1. So cosine of 60 degrees, quantity squared plus, well, we're given what sine of 60 degrees is. So let's write that ratio size as √3/2. That quantity squared is equal to 1. So cosine of 60 degrees, quantity squared plus, let's square √3/2. So squaring √3, we get 3. All over the square root of 2, we get 4 equals 1. We can isolate cosine of 60 degrees quantity squared by subtracting 3/4 on both sides. If I subtract 3/4 on both sides, I'm going to get a common denominator on the other side. I can rewrite 1 as 4/4, so 4/4 minus 3/4. 1/4 minus 3/4 is 2/4. That's a quantity squared there on the cosine of 60 degrees. I can simplify that, but I notice that I don't want to right now, because if I do, I'm going to have to rationalize the denominator. So let's take the square root of both sides. And so from there, we get that cosine of 60 degrees is equal to, well, the square root of fraction is the same thing as the square root of the numerator. So square root of 2 all over the square root of the denominator, but square root of 4 is 2. So we were able to figure out what cosine of 60 degrees is. Part C says we're looking at secant of pi6. So let's rewrite pi6 in terms of degrees, because we have degrees before. So secant of pi6. So if we look at pi6, recall to rewrite this in degrees, We multiply the radian by 180 degrees, all over pi. So our pi's cancel out. And we have 180 degrees over 6. Well, 6 goes into 180 30 times. So secant of pi 6 is the same thing as secant of 30 degrees. Rewriting secant in terms of cosine, this is 1 over cosine of 30 degrees. But we found that cosine of 30 degrees in part A was root 3 over 2. So we can rewrite that as 1 all over root 3 over 2. So let's do invert multiplying. So we get this is the same thing as 2 over root 3. And then rationalizing our denominator, multiplying by root 3 over root 3, we get 2 root 3 all over 3. So go ahead and let's have you guys try it. So try it number 2.
Professor, I have a question about B.
Okay.
So when we did cosine 60 degrees squared and then we subtracted the 3/4 from the 4/4, would it not be 1/4 instead
You're
of
right.
2/4?
You're right. I don't know why I did that. Yeah. Yeah, so 4/4 minus 1/4. Sorry, 4/4 minus 3/4 is 1/4. Thank you for stopping me and doing that. It's 1/4. So that's going to change things a little bit. So cosine of 60 degrees square root of 1 is going to be 1. So cosine of 60 degrees should be 1/2. Thank you for catching that. So you guys try it now. See if you can use what we've been doing to figure out what cosecant of pi thirds is. So you can use part A, B, and C. There are answers there if you need to for that piece. Okay, so you should have paused the video if you were watching this and take the moment to try cosecant of pi thirds. That with the other try it beforehand, you're going to upload again into the Canvas assignment for this week that I'll create. One more example, and then we'll be done with this section. So the next example says simplify each expression. Well, we only have one in front of us for a given value of x. Assume that theta is an acute angle. So we want to look at this, and all we want to do is we want to substitute in this case, what we're given for x. And we're given x here is equal to 4/3 sine theta, and we're going to go in and replace it wherever we see an x in this expression. And we have the square root of 16 minus 9 times x, but x in our case is 4/3 sine theta. And then it says we're going to square that x. So squaring that 4/3 sine theta. So let's simplify this a little bit. So we have 16 minus 9. But if we square 4/3, so squaring 4/3, we get 16 over 9 sine squared theta. Notice that our 9s cancel with one another. And so we're given here the square root of 16 minus 16 sine squared theta. Unfortunately, we can't just break this down. I see that 16 is a perfect squared and 16 minus sine squared theta is a perfect square, but we have that subtraction in between. We can, though, factor out that 16 from both of those terms and make it multiplication underneath the radical. So we have 16 times 1 minus sine squared theta underneath the radical. And so let's go back to our trigonometric identity. Cosine squared theta plus sine squared theta is equal to 1. You should start being able to recognize things that are like similar to this. So notice here, if I subtract sine squared theta on both sides of this Pythagorean trigonometric identity, that would give me cosine squared theta. Cosine squared theta is the same thing as 1 minus sine squared theta. And so notice inside the radical, inside that parentheses is 1 minus sine squared theta. So I can break that down as the square root of 16 times 1 minus sine squared theta is the same thing as cosine squared theta. Now that we have gotten it, that we have the square root and it's of a product of perfect squares, we can use rules of radicals. And this is the same thing as the square root of 16 times the square root of cosine squared theta. So the square root of 16 is 4, and the square root of cosine squared theta is cosine theta. Okay, so we've taken that expression and rewritten it in terms of the trigonometric function with the acute angle theta. So that is for our textbook. The rest of, or that is 7.2.